Hello everyone. For the course of ENGG851 Engineering Research Methods, I am Ahmed Hussain and this is my presentation for FRP composites used in reinforced concrete structures. Within this presentation, I'm going to tell you basically about what FRPs are, how I went through a literature review of FRPs used for reinforced concrete structures, which will help us to develop a research question and then a research design that will enable us to answer that question. We will analyze that design and come up with recommendations of how that design can be improved. Without further ado, uh, we will begin by an introduction of what FRPs really are. In its simplest form, a fiber reinforced polymer composite is a polymer matrix which is reinforced with fibers. You might be familiar with its most popular form, which is the carbon fiber. As you know that um, carbon fiber has a lot of different applications within many different industries because of its desirable properties of strength and being lightweight and being cheap to produce. Similarly, within reinforced concrete structures, FRP composites are now being used because they have the same strength as steel with only 1/4 of the weight, which makes it very desirable, along with the heat and electrical insulation that they bring along. Now, within reinforced concrete structures, the most common method of FRP um, application is the retrofit method, which involves just applying epoxy resin onto the surface of the RC structure and then applying FRP sheets along the epoxy resin. Now, it is a cheap and effective method, but it is non-invasive, and the latest research that is going on is focused on invasive methods, which includes deep embedment, ultra high performance fiber reinforced concrete, and textile reinforced mortar. Now, within these three, among these three, deep embedment and textile reinforced mortar are the ones that really piqued my interest and the ones that I decided to carry forward within my literature review. Now, before the literature review, the question that I came up with based on the many different techniques that I saw is what is the comparative flexural strengthening capability of textile reinforced mortar and deep embedded fiber reinforced polymer composites when applied to reinforced concrete bridge beams? Now, that might sound like a mouthful, but after we go through the literature review section, I'm sure it will make much more sense. Now, within the literature review, I went through about 20 publications that were focused in within this pocket of research, and that enabled me to develop a mind map. This is what my mind map actually looked like. The central idea surrounded by the different types of strengthenings that were researched upon, the type of reinforced concrete elements that the researchers used, and the different types of FRP materials that were the focus of the research. Now, among these, like I mentioned, that textile reinforced mortar and deep embedment are the ones that I chose to carry forward. And the type of RC, the reinforced concrete structures that I decided to work on was bridge beams. The reason for selecting bridges was, as a civil engineer, I believe that bridges are one of the finest marvels created by engineers. And as technology improves and we are more focused towards sustainability, it is better for the society and the environment if existing bridges are strengthened rather than new structures are made from scratch. So that was my motivation. Now, the relevant research was used as an inspiration for the design that I came up with. Out of all the studies that I researched on, I am going to take you to the two most influential ones. The first was by Zia et al. In 2018, who worked on the deep embedment technique of the FRPs, and they used it to monitor the shear strengthening, and they used it on bridge slabs. They came up with a patented way to drill holes onto the deck slabs of the bridges and then insert FRP rods directly into the bridge, into the shear plane, and then they were able to monitor the shear strengthening capability of the FRP rods using a standard 3-point loading test. Now, it was discovered that the failure shifted from a brittle shear to a ductile flexure, which was expected. And quite trivially, they also found that if you increase the number of FRP rods that were used, or you increase the diameter of the rods, the shear capacity increased. But that was pretty trivial. Now, for the future, they proposed a two-way design approach where where the shear capacity and the flexural capacity can both be studied separately, and then they could be compared of how effective the FRP rods can be. The second work that I uh, that was most influential on my research design was by Herbert in 2017, who studied the strengthening of bridge structures, mainly the bridge decks and the slabs and the beams, for shear strengthening, and they used carbon textile reinforced mortar for their study. Now, this was very interesting because unlike the FRP rods or the textile sheets, the textile reinforced mortar can be incorporated directly with the concrete structure itself, because the matrix or the layer that adheres itself to the structure is made of mortar, and it is the same matrix as the reinforced concrete structure. It provides a much better chance of achieving full scale strengthening rather than using epoxy resins. They also used a 3-point loading mechanism, and they naturally found a considerable increase in shear capacity. And for the future, they envisioned using an anchoring technique to see how the shear capacity could be further increased using anchoring techniques such as the U-jacketing method. Now, these two research papers influenced my research design, and if we revisit the research question that I just told you a few slides ago, it would make a lot more sense now that we are going to conduct a comparative flexural strengthening study between TRM versus deep embedded fiber reinforced polymer composites and apply that to bridge beams. So that is basically the research question that I came up with, and the research design is basically based on this question. For the research design, we came up with the idea of using 13 half-scale test beams. We decided to use half-scale test beams because the increased quantity on a lower scale would enable us to have more data points, which would make our findings more reliable. One of the beams would be the control beam naturally. 6 would be reinforced with FRPs, while the other 6 would be reinforced with TRM. We are going to use carbon fiber textile as the reinforcement simply because it is the most popular one. And we are going to use a 3-point loading test, much like most of the studies that I went through in my literature review. This image that I used from another research paper is of a 4-point bending test, but you can see that the mechanism is going to be the same. And we are going to direct the load at the center because that is going to increase the flexure at the highest. The testing parameters are going to be the number of reinforcement layers that we apply, the coating of the carbon fiber textile itself, which would affect the adhesion to the RC structure, and obviously the end anchorage or the U-jacketing method that Herbert talked about or suggested in his research paper. So this is a table of the samples that we will come up with. We believe that this amount of data points will enable us to have a reliable set of findings at the end. Before the application of the FRP or the TRM, I believe that short peening should be done so that adhesion can be maximized. The measurements that we are going to take include the load, the deflection of the beam, the increase in the respective capacity, and ultimately the failure mode. Now, for crack propagation, we are going to take regular intervaled photographs and then study the propagation of the cracks among the different samples. And at the end, we will be able to perform analytical calculations, such as calculating the effective stress for all of the samples. And this is definitely going to provide us with some insight of how the differing or varying parameters are going to affect the flexural capacity of these beams with both kind of reinforcements. Coming to the analysis of this proposed design, the advantages are that it follows a popular testing method. Therefore, it increases the comparative possibilities between the results. And we also have a considerable number of samples, which will enable us to achieve some level of precision. And I believe this is a new direction of research, because pitting FRPs against CTRM method is something that I did not see in any of the research papers as yet, and I believe this can be a new direction. The disadvantages, however, will be that it is a tried and tested method, the 3-point bending test, so it's not going to be anything new. It's not going to be innovative in terms of research design. And also that because we are comparing the flexural capacity increase by two very different methods, CTRM and FRPs, so it might be like comparing apples to oranges, where you cannot directly compare one to the other. And because it is a half scale model, the full scale findings can be different. They might be, they might not. That is something that can be looked at in the future. And at the end, we believe that this kind of design lacks some kind of analytical modeling. So in the future, perhaps some numerical analysis or some finite element analysis can be incorporated into this study to improve upon the results. Now, as I said, the recommendations are that we can verify these practical results with numerical modeling, and we can further improve this research with increased number of variables, particularly the adhesive matrix that is used. At the end, these are the references that I used for my research study. You are very welcome to visit any of them. And that is the end of my presentation. I hope you enjoyed watching it, and I hope that I was able to convey my research design and my research question effectively. I will see you all in the review section. So